webinar on the recent progress on silicon photonics research in India and elsewhere. Professor Bijoy Krishnadas obtained a master's degree in solid-state physics from Vidyasagar University, Midnapur, India, and a PhD degree in integrated optics from the University of Paderborn, Germany. Before his PhD research in Germany, Dr. Das started his research career in the area of integrated optics at the Microelectronics Center, IIT Kharagpur, for 3 years. He was an FRC postdoctoral fellow in the Graduate School of Engineering of Osaka University, Japan. Later, he joined as a postdoctoral researcher in the Center for Optical Technologies, Lehigh University, USA. In April 2005, he rejoined the Integrated Optics Group at the University of Paderborn as Wissenschaftlicher Mitarbeiter and continued his research on the integrated nonlinear optical devices. Since August 2006, Dr. Das has been associated with the Department of Electrical Engineering, IIT Madras, where he is presently holding a full professor position. He is one of the founding members of the Center for NEMS and Nanophotonics at IIT Madras and Chief Investigator of Silicon Photonics Center of Excellence, Center for Programmable Photonics Integrated Circuits and Systems, funded by the MEITY Government of India. A hearty welcome to you, sir.
Yeah. So thank you very much for your nice introduction. I'm also grateful to you for inviting me, giving me this opportunity to present some of our research work and also talk something related to my expertise area. And I'm also glad to see in the audience Dr. Suresh Nair. We know each other for a long time, and starting from my PhD career. And after that, with several committee also, many of my project review committee member was Dr. Nair. He has given his expert comments and guided us nicely. I must be grateful to him. And I think I'm also grateful to Miss Binu Jiju, I think, for reaching me and requesting me. I think I forgot to reply, and she was reminding me, and somehow I could manage the timing. So with this note, I just would like to share my screen because without slide, hopefully it would be difficult to present my work. So just if it is coming all right, just tell me so that I can continue. Is that visible, my screen? Yeah.
Yes, sir. Yes.
Yes.
Okay, fine.
You can put it in full screen, I think. Full screen mode.
Yes. So as I mentioned that I'll be talking about silicon photonics technology, what is the state of the art in India and elsewhere. And I have not given that title because that is already mentioned here. Specifically, I'll be focusing certain area which is very, very hot these days, so-called quantum photonic devices and circuit using silicon photonics technology, shift silicon photonics platform. And as mentioned by the in the introduction, that I have been worked at different parts of world, and also, of course, my starting point was IIT Kharagpur, where I started working in the area of lithium niobate integrated optics. I think Dr. Nair also expert in lithium niobate integrated optics, because that time, it is 90s, in the previous millennium, lithium niobate was considered as something very hot and could be the alternative to silicon for optics world. What silicon could do electronics, lithium niobate can do for optics. However, that thing reduced to academic interest today with some special application. for several decades, for first 2 decades at least in this millennium, only a discrete component like modulator, lithium high-speed modulator, that was commercialized, and that is actually widely used in telecom. But other than that, not much things happens as far as industry application is concerned. But very lately, again, this technology is coming back with a little bit of improved wafer level technology improvement, and it is getting momentum again back. So I think that's a good news for Dr. Nair, also me, because we started working on lithium niobate in the beginning. And then that thing, I continued that research almost 10 years, 1996 to 2006, and in several institutes, most of my part for PhD as well as my postdoc career. Then slowly, I realized that the lithium niobate technology is very good, very interesting, academically very interesting. A lot of things can be done, but because of technology is so expensive, no industry was coming forward to promote this, to invest money. Rather, silicon in the meantime, it somehow getting momentum by improved quality of wafers, optical grade wafers. So electronic grade wafers were available right from 1970s or so on. But because optical grade silicon substrate could not be manufactured, that's why photonic devices in silicon was a bit delayed. And over the years, technology improved, and good quality silicon substrate, both optical grade as well as electronic grade wafers are available. So that thing came up. Started in 1980s though, but slowly improved. And at the beginning of this millennium, around 2000 or 2001, that time it was just somehow technology was growing very fast. And I thought that because of my background in integrated optics, entire theory, technology, everything known for lithium niobate, but same theory is applicable to silicon photonics also. So I switched my area into silicon integrated photonics. And when I joined here in IIT Madras, I thought that I should scrap lithium niobate and we will start right from the beginning silicon photonics. And that time, frankly speaking, in India, I think no one seriously working on silicon integrated photonics. That because that technology, you know, that's a kind of microelectronics technology available few places in India, but switching over to photonics domain using those type of facilities was very challenging and also very daring, I would say. So I proposed a research proposal here in IIT Madras, and somehow it was widely accepted, and started working on silicon photonics right from the scratch. Okay, and before that, of course, before I started, I visited Ghent University, IMEC, that is actually a pioneer that time. They are actually promoting silicon photonics. I interacted with them, got some knowledge. Then I thought that let us try in India. So here joining in 2006, we started building a lab called Integrated Optoelectronics Lab. And that is in 2006, as I mentioned. And over the years, we did some progress. And then together, combining with other faculty members, research scientists here, we proposed a center for NEMS and nanophotonics. And that is in 2012, and they are one of the major component of the area is considered as a major contingent is silicon photonics. So that is a nano facility. A lot of technology process units we procure, and I was one of the founding member. And we progressed some work based on that. And recently we got a Center of Excellence funding for Center for Programmable Photonic Integrated Circuits. And that is how my career is there. So that is not only my career, I would say that this is the story of Indian silicon photonics, I would say, because we have started right from the beginning 2006 and then almost 15 years. Of course, very recently, I would not say, about 5-6 years back, I say Bangalore also, they have started silicon photonics research very seriously and they're doing good work also. So except these two places, I will show towards the end of my talk that there are many other places, a lot of young people joined in many institutes and research centers. However, they can't progress much. They are because of, not because of lack of some projects or funding, but because of the facilities, because the silicon photonics technology, again, you need very high-end technology, nanoscale dimension, accuracy, all those type of things are required. So facility is not available yet, even in academic institutes and company and industry, it's a long way to go. So that is the background I wanted to mention before I start my talk, so that you get a feeling that what about we are going for. Though I would be also presenting what all things going on around the globe, how fast they are moving, and how much we are lacking. That is very important for particularly young people like you, so that we can push for in this particular topic to convince various contingent in the country so that we can be a global competitor also. And there are some good hopes are coming forward. So I think things will be changing very fast now onwards because of the introduction of, I think, this Indian semiconductor mission and foundry, etc. is coming up. So a lot of hopes are there. And also I must be grateful to MEITI because they have given us substantial funding, actually, this to establish the center of excellence, about 30 crores to have a full-fledged silicon photonics technology development and prototyping startup, etc. I will be just covering few things for that. So before going into that, I will be just giving a little bit of historical background, how we progress, because that is very important. Why I am mentioning all this, why India is lacking, because it needs a lot of tenacity, a lot of determination, a lot of sacrifice required to reach to a certain objective, to obtain some certain output. So I will be just giving some overview very briefly, the path timeline, how we progressed. And we are now, I can say that at least we have the technology, we have the silicon photonics passive, some active devices we can fabricate, that is nearly international standard. So that's why I'm very much interested to show in front of you that is not very impossible. If you have some tenacity, it is very much possible, and you need to come forward and start working in this particular area, because that is basically, I would say this is a disruptive technology. I would say all area it is actually now manifesting. So after that, I will be just taking only one particular topic, which is very hot and promising, and industry is investing, but not products yet available in the market, but it will come anytime soon. Okay, that area I will be just giving some outline how that particular technology is coming and how far we are from the commercialization. And then I will go a little bit deep into the, for example, all the silicon photonics, it means actually photonic integrated circuit. So circuit means you have combination of components, you have to create a circuit so that you get a particular functionality out of the entire photonic chip. So that integrated electronics, there's a fundamental building block is like a transistor. So transistor is the major fundamental building block, and you can just keep on increasing the number of transistors to get a greater and complex functionalities. Similarly, it is also thought that if we can get a certain building block similar to transistor, so that actually you can scale up complexity of integrated photonic circuit, and you can get all the functionalities at the speed of light using photonic signal processing or optical signal processing. So that type of component, it is not yet found so far. However, one building block it's called silicon, just micro ring resonator. Micro ring resonator, using only the micro ring resonator, you can perform many functions. It can be programmed for achieving different functionalities. So you can get also some kind of field programmable circuit, photonic domain. We call it as a field programmable photonic circuit, a photonic gate array, field programmable photonic gate array. It is analogous to your electronic FPGA, field programmable gate array. So here we will call photonic gate array. So that gate can be considered, the ring resonator, programmable ring resonator can be considered as one of the unit of the gate. Similarly, another building block is Mach Zehnder interferometer. That is also considered, that is used also for such a building block, photonic gate. And I will be just also covering some area in that particular direction. But this micro ring resonator and Mach Zehnder interferometer both are useful for all photonic integrated circuit, including what I am trying to target to give you some outline for quantum photonics technology also. And another thing I will be just discussing, this is our very own design. So concept is old, distributed Bragg reflector, but this distributed Bragg reflector we have somehow modified the design, and that design somewhat giving certain characteristics, something called extinction, filter extinction, the stop band filter characteristics it will give, at that particular performance is very much promising for quantum photonics technology, which was not reported before. The results we have recently actually reported, that is actually something world record, and which could be widely useful for on-chip quantum photonic applications. That thing I will be just covering a little bit, and then summary and conclusions. So before going into that particular area, I would like to give you some flash of very recent news. So first thing, if you see, when we talk about silicon photonics, it is nothing but, it is not only photonics, not only optics or integrated optics. It means electronics and photonics, silicon electronics and silicon photonics, that combined together actually gives you so-called photonic integrated circuit. So this photonic integrated circuit, that is the ultimate objective you want for scaling up and to be useful, similar to what we achieve in integrated circuit, electronic integrated circuit. But remember that it is not growing or being developed just to completely replace the electronic integrated circuit. That is not the case. Rather, it is being used just to complement electronic integrated circuit, because there are some limitations, some bottleneck is there in integrated electronic circuits for wider applications. Where those type of bottlenecks are there, that bottlenecks performance can be improved and enormously improved if you use photonic integrated circuit, I mean silicon based photonic integrated circuit. So this silicon photonic integrated circuit, whenever you are studying, parallelly you need to have a very good knowledge of electronics integrated circuit as VLSI technology. That is also you need. So it should go side by side. Otherwise, you will be completely in dark what for silicon photonic integrated circuit and where it can be used and how it can be used. So that is how the background of photonic integrated circuit comes, and that terminology is widely used now. When we call photonic integrated circuit, it means mainly for silicon photonics and silicon electronics. But of course, I should not overlook other things also. It is not only silicon photonics and silicon electronics. Sometimes photonic integrated circuit, as I mentioned, lithium niobate based photonic integrated circuit, also called this photonic integrated circuit, but less popular, and another indium phosphide based. They are also, at this point of time, India phosphide-based photonic integrated circuit market price, share is much higher than silicon photonics, but that cannot go beyond a certain limit. Theoretically, technologically, it is showing all promise that silicon photonics, it will grow, it will capture almost entire photonic integrated circuit market. So as I promised that I wanted to give you some class here. It is given very recently, last year, 2021 March. So Intel Corporation announced in March 2020 that it successfully integrated its 1.6 terabit per second silicon photonics engine. It's called silicon photonics engine. So mainly its performance is, its functionality is that you need to interface a electronic processor, electronic memory, electronic processor to interface with a high-speed interconnect optical fiber and so on. So that's why it is some kind of engine. It actually converts electrical information into optical information. This engine actually, that is why it is called engine, silicon photonics engine. So that engine can pump data from your processor or computer board, motherboard, or whatever things are parallel process computer, high performance computer, you can imagine. So from there, if you want to communicate that data optically, that means that electrical data you have to convert into optical data, and then once it is optical, you can enjoy the optical frequency. That's when it's about 200 terahertz. So and 200 terahertz is the frequency, but you can enjoy a bandwidth of about 40 terahertz, something like that, about 1/5 of the frequency you can use as a bandwidth. So using that high frequency, high bandwidth, you can actually transmit data at a higher rate. So they reported about, so 12.8 terabit programmable Ethernet switch that demonstrated. Okay. But it is in March 2020. I must remind you that Intel started working on silicon photonics right from the beginning of this millennium. Their research started in 2000 itself, and it took 16 years, about 16 years to actually launch their first product of this type of transceiver. That time it was 100 Gbps. Now, within 4 years, it has gone to 12.8 Tbps, terabit per second. So you can imagine, so once their background, their basis infrastructure, everything set, they are moving very fast. And a little bit later, in August 18, 2020, Xanadu is a startup company. They actually partner with IMEC. IMEC is actually very advanced R&D foundry where you can do a lot of advanced level electronic integrated circuit research, device research, and all the new type of technology coming up that is actually starting from Intel, IBM, all big giants. They do their advanced level research in IMEC or some other foundry, TSMC, like their foundries. And once they established, optimized, and they will be used for production purpose. So the Xanadu is a startup, and they collaborated with IMEC, and they are developing quantum photonics chips for computing, and quantum computing processors. So photon can be used as a qubit, and qubit is widely used for superconducting, using superconducting nanowire. So qubit is basically superconducting qubit nowadays people are using for quantum computation. For IBM, Google, all those people are doing. But the Xanadu is coming up with a silicon photonics technology, CMOS technology. So they have in their roadmap, their timeline, they included that within 2-3 years they will be able to demonstrate silicon photonics for quantum computation. So this is the space. So initially, actually, silicon photonics was being developed just for to be used as a silicon photonics engine, so that high-speed communication can be possible within data centers, board to board, rack to rack, and maybe sometimes possible within the chip. Within the chip also, you can just use wherever some bandwidth limitation is there. So you can convert electrical signal into optical signal and use optical waveguide, convert back into electrical, and then process and feed into another processor, and so on chip. So these are the initial target, and that is how all the investment came. And later on, it is being explored so that that same technology can be used and for the development of quantum photonic circuits and many other applications. So I want to give you highlight, other than that silicon photonics engine, what other areas are growing, because that is very important for people like us as researcher, and for our future career also, because whatever silicon photonics engine, that is already almost optimized and it is product is already in the market, but that does not mean that you cannot do, you don't have much scope for research. You do have, but many other area you can contribute with your novel idea, novel design, novel concept, everything can be come out. So to understand that, I want to give you a highlight here in this slide, that what all are there in silicon photonics technology. What is available whenever you want to make a silicon photonic circuit or photonic integrated circuit in a commercial foundry or in the lab level also, what all things you need to consider and what are the constant, I mean to say, what are the technology available, what is the using technology, what best device you can fabricate, and of course the considering all the constant or limitations. So one advantage, as I mentioned, that it is actually CMOS compatible. That means whatever infrastructure used for electronics industry, IC manufacturing, same infrastructure would be good enough for your photonic integrated circuits if you are using silicon platform. That is the advantage for silicon. So same infrastructure, you don't need a completely different technology process to implement, like lithium metal, for example. You need completely different technology for implementing a photonic integrated circuit in lithium metal. Indium phosphide, it's a completely different technology. So it cannot be fabricated in standard silicon CMOS foundries. But this silicon photonics, what I'm just trying to mention here, they can be fabricated in normally silicon CMOS foundries. So that is the advantage. Same technology, you can just a little bit modify and then you can use. And what all we can do here, it is something I have borrowed just a cartoon figure from Advanced Micro Foundry Singapore. Okay, they have a silicon photonics foundry, and how they are using their CMOS technology to demonstrate different important component in silicon on insulator platform. What is that silicon and insulator? You have a silicon substrate, and then you have some barium oxide layer, and in the top layer there will be device layer will be there. Okay, so this device layer actually called as a SOI, silicon on insulator, silicon device layer on insulator. So this silicon layer normally used for our so-called CMOS circuits. You can demonstrate for particularly all the digital ICs, everything analog and digital ICs, they are fabricated using the silicon on insulator so that you can get a better performance. But there are some limitations. I'm not going into that details. Okay, sorry for that. So now this device layer, what you can do, you just use the same technology. You can have, for example, this type of structure, so-called, okay, you have your, let us consider this one. So this is a silicon layer and it is like a reef structure, you see. And then this reef structure, it is a silicon and bottom is oxide, top can be also oxide. Then this structure, if you see, particularly if you consider an optical communication band, 1550 nanometer used for fiber optic communication, that 1550 nanometer wavelength band is transparent in silicon. So the photon energy is much lower than the band gap of the silicon. So it can be if you, as long as you are using silicon, this substrate layer as a kind of intrinsic and photon energy lower than the band gap, that particular laser source or light wave, the silicon substrate is not a semiconductor and it is a dielectric material. So you know dielectric material, you can design properly, cross section you can design such that it can give you like an optical waveguide. So light can be confined through total internal reflection and can be confined in a mode, and that can be propagated. So that type of waveguide you can fabricate. And being silicon, what you could do, okay, you have an intrinsic region. Some region, what you do, one side you can dope p type, another side you can dope n type. So you can get some kind of diode across the waveguide. Waveguide propagation direction is there, and across that you can get a diode. So diode, you know, if you just control the bias, forward bias or reverse bias, the depletion region that is in the core of the waveguide, that region you can actually control by controlling the bias. What happens if you control the depletion region? That means you are somehow controlling certain carrier electron in the n side and hole in the p side. You can control. If you can control that electron and holes in the core region of the guided waveguide, guided modes are propagated through waveguide, that electron free carrier density, when it is changed, that you will observe certain kind of refractive index change. Okay, so that normally higher the concentration, free carrier concentration, refractive index will be reduced. So refractive index reduced means guided mode will experience different type of phase velocity. So in this way, you can actually design a modulator. What this modulator can do, modulator, you know, that actually converts electrical signal into optical signal. That can be done here. So that means this conversion, electrical to optical conversion, you can do. You need only a carrier, optical carrier, and then electrical signal comes through this wires. You can control this data can come here. I just briefly outlining. There are a lot of complexity will be there inside, but you can encode the data. So that type of device, modulator, you can fabricate in silicon. And same way, you know, whenever you are using 1550 nanometer as a silicon as a dielectric material, you cannot use silicon diode as a photodetector, because for photodetector, you know, that light actually should be, photon energy should be absorbed and electron hole pair should be generated, and then you can get a photocurrent, and depending on the photocurrent you get a photodetector. Or you can whatever optical signal is there, modulated data is there, using photodetector you can decode, you can convert back your optical signal into electrical signal. So two things is you need for in an optical engine, right? You have to convert electrical to optical and then optical to back into electrical. So modulator and photodetector, these are the two things. Modulator you can use fabricate using CMOS technology here, and photodetector normally silicon diode cannot be used because the photon energy is lower, band gap is higher, so you cannot create electron hole pair with light is propagating. So that is what unwanted for any waveguide and optical waveguide if you want to fabricate in silicon. So that's why people use germanium, where actually you can get a band gap is much lower, about 0.65 or 0.7 electron volt, much lower than the silicon, where band gap is 1.12 electron volt. Sometimes germanium as well as silicon germanium, you can little bit engineer the band gap, and you can use as a photodiode for 1550 nanometer. So photodetector can be done. So modulator, photodetector can be done. And normal waveguide, of course, you can fabricate, you can design all the passive devices, power splitter, ring resonator, Mach interferometer, everything on chip you can fabricate once you can implement a very good waveguide. Okay. And only one problem is that inside silicon, it is very difficult to integrate, to fabricate a laser diode monolithically, because silicon is an indirect bandgap semiconductor. That is actually a problem. Okay, so that thing people are just trying to go for a heterogeneous integration, flip chip bonding, different type of technology being developed, so that in a chip you need only one or two laser sources. You can just pick and place and you can bond, and that way people are solving at this point of time. But at the same time, people are also working on to grow actually 3-5 material direct bandgap semiconductor, so that laser diode can be fabricated. And one more thing, you see, normally any integrated circuits, you use 3 different materials. One is you need semiconductor, you need conductor for connecting wires, and you need also insulator to isolate one device to another device. You can have a bias, etc. All these type of things can make. So these three different type of things are required for your electronic circuit. In photonic circuit also you can see you need a semiconductor in dielectric material, semiconductor like silicon you are using, and you have bias, all these metal interconnects you need, and also top also you need oxide layer so that you can get a cladding. In the top cladding, lower refractive index, silicon is the higher refractive index, and silicon in the bottom also lower refractive index. So core region you need higher refractive index, that is silicon, and surrounding region you need oxide. Okay. Now problem is that one important thing that, okay, we are talking about only 1550 nanometer. That is a communication, that is optical engine, all this type of thing is good. That 1550 nanometer, that is widely used for third telecommunication window, that's not a problem. But if you want to explore the same technology for other applications, you may be interested to go beyond 1550 nanometer, maybe other spectrum, other wavelength spectrum, right? So in that case, how this technology will be useful? So, you know, if I just try to see a silicon, that is actually widely used as a core material. You see, this is the wavelength, it is shown in the x-axis, and this is the transparent region it is shown. That means for silicon, if you see about 1 micron wavelength to about 8.5 micrometer wavelength, all the electromagnetic wave within this wavelength band, that is transparent. So that means you don't need to restrict yourself only for 1550 nanometer, and only you should restrict yourself only for optical engine. You can think of any other device also using silicon as a core material for other applications. Visible region also you can use, infrared, mid-infrared, far infrared for spectroscopy applications, many other application you can think of. But however, one more restriction is there. You know, silicon is a core region, core of the waveguide, but outside silicon core, there will be, you need a dielectric. Native oxide silica is used, but in case of silica, silicon dioxide, you see transparency is very poor. Poor means it is very good transparent at visible to maybe infrared and near infrared up to about 3.5 micrometer, it is propagating. So whenever you are using a cladding, silicon oxide cladding, you know, in a guided mode, that mode confined within the core we say, but there is a evanescent tail will be there that will penetrate into the cladding. So cladding region, if it is not transparent, suppose you are using core, silicon core, you think that, okay, core region, it is transparent 6 micron, but whatever the evanescent tail will be penetrated to the silicon oxide, that will be actually attenuated, because it is not transparent silicon. So not only silicon core and silica, people are thinking another material which is also CMOS compatible, that is called silicon nitride. So silicon nitride, it's a bit of wider band gap, and also it is CMOS compatible, and its refractive index is also not like as high as silicon, because you know, core material higher refractive index means you can make a tighter confined guided mode. Your waveguide size, cross section size can be very small. Smaller the cross section, you can make a smaller footprint of the device, ring resonator, Mach interferometer, etc. And you can go for large scale integration without any adding cost, etc. So that is one advantage if you have a core material with very high refractive index. Silicon, for example, at 1550 nanometer, refractive index is around 3.5. So that's one of the highest ever possible material you get, where refractive index is such high, and you can have a very tightly confined or very small cross section waveguide you can design, light can be confined. Silicon nitride relatively lower, this 3.5 at 1550, silicon nitride refractive index at 1550 nanometer is in the order of 2. So here if you see silicon nitride, the silicon nitride transparency, it can come well inside a visible region. So about 450 nanometer, it can start, it is transparent, and then it can go up to 7. So you can imagine silicon and silicon nitride, you can penetrate at least up to 7 micrometer. And also silicon nitride, people use silicon nitride, sometimes core material used for visible region. Still silicon nitride can be core, and silica can be cladding if you are interested to design your device in the visible region also. So that is the all type of material combination is available for CMOS technology, and you have some freedom of going beyond your communication band for other applications. So what are the other applications we are just seeing around the world? People are doing investment and R&D in academic institute, industry. So we just try to summarize here in this cartoon: photonic integrated circuit. One is you can think of quantum computation and key distribution. So quantum computation, you can use 1550 nanometer, of course, wavelength, but you can think of some other application, because sometimes some visible regions you get a better yield. For example, certain kind of hybrid type of quantum processor where you can have both superconducting qubit. You want to convert superconducting qubit into your optical qubit. In that case, visible region wavelength will be useful. So in that case, that is a very good applications here. And also you can think of microwave photonics area, where you can use for advanced radar system. Nowadays, people are talking about quantum radar also, multiband quantum radar systems. They can be fabricated, they can be designed and demonstrated, and some progress already made. I think many industry, they are doing what we know that, but they are not publishing many papers because this is something related to defense, security, etc. is there. But you can find a lot of patents in this area also using photonic integrated circuits. And then also, microwave photonics, another application, 5G, 6G, all those type of thing, higher bandwidth. It is about 25, up to 25, 26 gigahertz frequency range. It is used for wireless communication in your mobile, whatever the 5G communication coming up. So there actually the silicon photonics are also used, because sometimes, in the microwave signal, it's very difficult to process. It's a bulky devices. We need to handle. So instead of that, if you part of the processing, you can do using silicon photonics. How it can be done? You can just convert microwave signal into optical signal, same way using modulator, and then you can process optically, do important part of operation, filtering, and also one of the major thing is that filtering, and sometimes also you can use them for particularly antenna purpose, for beam steering purpose. And nowadays also people are coming associated 5G technology, LiDAR technology, all those type of things are coming. And this is actually what I mentioned, that is already successful in the industry. High-speed optical transceiver, that is one was in the terabit per second it is available. And also now people are doing a lot of research so that it can have on-chip optical interconnect within the chip. Within the chip, where actually you see the electrical interconnect bottleneck, that time you can use your optical interconnect converting things. So that area, theoretically, it has been shown that it is actually very useful. You can speed up you can have a very high speed optical interconnect within the chip. And also the thing is that some technical problem is there, because although we say that you are using CMOS technology completely, all the process steps you are borrowing from CMOS foundry infrastructure, that is fine. But one important bottleneck is that if you want to co-integrate electronics and photonics, slightly different dimension of the device layer is required. Sometimes dimension and all other additional material probably require, where you may not need this germanium photodetector type, this type of things you may not need in your electronic circuitry also. So little bit additional steps required where electronics IC is not required. Another major important thing is that whenever you are trying to co-integrate your electronics and photonics, then a lot of thermal management is required, because electronic circuit, they can throw a lot of heats, and that heat will go for a crosstalk to your photonics devices. So you need a very good insulation, very good thermal radiations, all those type of things. So those type of technology being developed, and that can go a long way for R&D. And good part is that theoretically it is being shown that if we come out with a good design and technology bit input, then actually this on-chip optical interconnect is very much will come soon. And then lab on chip biomedical applications, also sensing application. Once you get an integrator, I think if you see a lot of people prefer to work in this area also, because biomedical application is a never ending story. All the as long as human civilization will stay there, they need the healthcare, biomedical things required. So people are also using, exploiting this silicon photonics technology for biomedical applications. Okay. So this is the background. So all different areas are there, and we at IIT Madras actually we don't have foundry like process all those type of things, but we have the technology to fabricate this type of waveguide, this type of modulator, and some kind of ring resonator, Mach Zehnder interferometer, using our nano Center for NIMS nano and nanophotonics facilities. So, so that facility we exploited, and we have developed the process line to fabricate silicon photonics devices. And that process line, the steps are maybe different, but all the process, all the design we do such that if you go for a complex circuit fabrication from a foundry, large scale integration, you can have few thousands components will be integrated. So in that case, whatever design, their PDK process design kit available in the commercial foundry, we just use the same design rule so that we can demonstrate in our lab level, and finally for a complex circuit, which is we are not capable for scaling, that time we can get the chip fabricated in a commercial foundry, and that process is going on. And yeah, so with using this process, some of the photograph it is shown here, silicon photonics devices. I just mentioned earlier that Mach Zehnder interferometer. This is something you consider Mach Zehnder interferometer, 2 input ports, 2 output ports. You can launch in one ports, and then there is a 3 dB power splitter. You can split them and you can combine them, and you can get 2 input ports, 2 output ports. And in between, you can integrate a lot of active elements so that it can be useful. It can be used as a modulator, intensity modulator, phase modulator, all those type of things can be done. And another important device is ring resonator, that is also fabricated. You see, this is actually a 10 micrometer ring. And this is waveguide. This waveguide dimension is about in the order of 500 nanometer. And this is the bus waveguide. You see, here you see the waveguide, you don't have input and output. It is a ring. But if you have a bus waveguide that is passing very close by to this ring, then light guiding through the bus waveguide, that can be evanescently coupled, and resonant wavelength can be stored here. So this is a kind of resonator. You can actually at a resonant wavelength inside the ring, a lot of power will be stored there. And you can just control this phase of the ring. Then you can use this as a modulator. You can use as a switch. You can use as a filter. You can program this thing. This Mach Zehnder interferometer and this micro ring resonator. You can have a different type of phase control, different part, and you can program them, and you can get a multiple functions. And then if you just cleverly, you can design them, you can cascade them, you can get a very complicated and very useful applications for optical signal processing purpose. So we could actually fabricate such a Mach Zehnder interferometer. Here you see that there are 5 different phase shifters we could integrate, and we characterized successfully, and they are actually published in a good journal also, and a lot of hope. We are also taking this one to go for this type of design we are using for developing a field programmable photonic gate array, so that a particular programmable chip you can fabricate, you can give a certain code, certain program to get certain functionalities. Now you want a different functionality, you can just reconfigure and you can get a different functionality. That is how field programmable photonic gate array is there. And another DVR structure also fabricated. I think I am a little bit running late. I will be a little bit going fast. So how much time I have? I think I can finish by. I think Dr. Nair, you are.
Yeah, you can focus on the applications, and because these details, sure. I think the students may not. Yeah.
Sure, fine. I'll just quickly go through that. The other process also we developed. And also, we see, as I mentioned, I wanted to tell, we have started in 2006, and different timeline we could demonstrated. Say first, we first got our CNNP Center for NEMS and Nanophotonics 2012, and then we have demonstrated first high-Q micro-ring resonator. High-Q means in the order of 10 to the power 5, we demonstrated in 2017, and then first project we got from DST for quantum photonic research in 2017, and then to 2020 we fabricated a DBR filter which could keep extinction of, it is shown here 60 dB. Currently we are hitting 65 dB. That is actually useful for quantum photonic application on chip, that is world record, but ultimately we have to reach up to 100 dB extinction. So hopefully we'll be getting that within a month or so, within few months, I would say. And then at the end, we have our, this last year, 2021, January, we got the Center for Programmable Photonic Circuits, about 30 crore project. And just want to give that what we are doing here in our center. So it is just commitment is that we should have, because we need a lot of manpower development, because now semiconductor industry coming, so we need a lot of skilled personalities processing everything. So we have committed that at least per year, overall, just for 5 years, we should have a very high skilled 50 manpower, at least 50 PhD students should be graduated from the center within 5 years. That is our goal. And 3 different applications based on so-called field programmable photonic gate array we planned. One application we consider for quantum photonic processor for computation purpose, and then quantum key distribution chip, another thing, and another chip for microwave photonic filters, microwave applications, particularly beam steering, those type of applications. We are just considering 3 different application commitment. And also we also planned for some startups, some technology transfers, so that prototype development, technology transfer, and in that phase we need a very good packaging facility required. We have an industry collaborator, SI2 Microsystems, that is located in Bangalore. They are professional. They have a very good facility for IC packaging, integrated electronic circuit packaging. Now their foreign counterpart, they know how to do photonics chip packaging also. So they want to here establish the silicon photonics chip packaging, co-packaging. That means electronics as well as photonics chip together, co-packaging system in package. They want to extend their facility, and they are collaborating with us, and they are our partner basically. Sponsoring agency, we would say. They are facilitating. So together we are developing the design rule and for packaging, because the packaging rule is not established yet. Whole world they are going for different type of design rules. So we thought that we can start with working here, so that packaging design rule can be developed, and also testing, and also whatever certification, all those type of things we will be doing. And for that we have expertise also in different area, from device, electronic device, to programming circuit people. For example, Sarenak Sivartacheres is well known in processing and device processing, and Janak Raman. So they are working in the area of circuit and all this driver circuit co-integration with photonics chip. He is helping us. And also Deepa Venkatesh, she established here a world-class communication laboratory. So what is our idea is that whatever prototype we are developing, we can also use for system level applications. So they have a test bed for high-speed communication system, etc. That will be useful. Anil Pravakar, he is a well-known face in India for quantum photonics. So he is also collaborating with us. He is mostly working on fiber optics and all this QKD system he is developing, and we are developing a chip, QKD chip. So whatever demo QKD chip will be developed, he can demonstrate that. And Professor Amitav Das, they are microelectronics background, all the processing related things. And this is Professor Christopher. He is a former DRDO chief. He is now faculty or colleague. He is actually advising from the top, though he is sitting here at the bottom, but actually he's in the top. He is actually helping us to bringing all the industry together and collaboration, etc. So he's like an advisor. Yeah. And we do have international collaborators. You see, Bim Bogers, actually, he is the guy. I suppose that he is the first one who did actually real silicon photonics PhD work. And based on this thesis, IMEC actually started multi-project wafer runs. And even before I came to IIT Madras, I visited that place. And that time he was he just completed his PhD. He was showing IMEC everything. And still, since then, we are friends, and he is helping us to develop our silicon photonics technology. He already gave a webinar talk for us also. And very recently, we have a new collaborator, Professor Jose Kapmani, who is pioneer in microwave photonics, in photonic integrated circuits, microwave photonics, signal processing, etc. purpose. He is also our collaborator. Professor Sayan Mukherjee, he is one of the pioneer in quantum photonics. So weekly basis meetings, everything we are going on. So we are somewhat all the experts together. We are working and somewhat progressing slowly but steadily. And fortunately, we have a very so now you say that we have the facility and we have the huge number of students we are getting also. And you see, it's Arnav Goswami, he's the chief technology officer, and then there are research associate, technology officers are there. And you count from here to here, all are PhD students. There are 10 PhD students. All of them, their actual language is silicon photonics. All of them, some of them are doing fabrication, some of them are doing design, and some are going for tape out. So it is a kind of huge team. Okay, so and also we have some administrative secretary, logistics secretary. So it is like a something. It's a complete package we have, and we are continuing our work in that way. As I mentioned, I will be talking a little bit about how silicon photonics technology is being exploited for quantum photonic applications. Okay, so here you see this is a kind of chip, and recently proposed and demonstrated also. It is a representative one. People have already demonstrated much more complex design. So what actually there for a quantum photonic processor, you need, you know, that for a quantum photonic circuits, you need quantum state of a photon. So you need a photon source. And that is possible using silicon photonics technology. It is just shown as a spiral waveguide. It's a waveguide. Just to get a little bit longer length, it is spiraled, so that footprint will be smaller. And you can use kind of spontaneous four-way mixing process. Spontaneous four-way mixing process. That means two palm photons, they will be combined together and they will be generating two daughter photons. Those two daughter photons, they will have some kind of correlation in terms of quantum state. So you manipulate that quantum state for getting all the quantum information processing. And for those quantum information processing, what you need basically, you need some kind of Mach Zehnder interferometer, phase shifter. These are these yellow lines, they are phase shifters. You can have a micro heaters. You just send some current, and because of the Joule heating, the waveguide section will be heated up, and through thermo-optic effect, some refractive index will be changed, and propagating photons, they will see some kind of phase or momentum change. Okay, so all these things actually it's commonly used in your silicon photonics engine, and this type of waveguide is used for silicon photonics engine. And what is extra needed, you know, this pump removal filter. You know, this, when I'm talking that two photons can combine to give rise to a two daughter photons, entangled photon pairs, and you can use them. They are actually completely probabilistic, and there you need a circuit to make them deterministic. To find when is the one single photon is generating, you have to just identify that the time time slot, and you can say that within that time slot that channel is carrying some photon or not. That thing also we should be able to control, even though process is deterministic, probabilistic. And not only probabilistic, it is the probability is very poor. It's a Chi3 process, and it's a rarely occurs. That's why you need very high intense pump to generate your photons. To maybe 1 billion pump photon you inject, maybe one entangled photon pair will be generated out of 1 billion. So you have to use that one photon out of 1 billion pump photon, and maybe almost everything unused. That unused pump you have to remove immediately from the source. Otherwise, what will happen? That unused pump, as it propagates through the circuit, it will keep on creating quantum noise. So it is one technological problem. People use a lot of quantum coding, etc., so that you can get your whatever output. But this is what I mean to say, that this filter, if you cannot fabricate on chip, and that filter has to be very, very good one. It has to be highly extinct, 100 dB extinction required, and also this filter should pass the daughter photon. So it has to be designed very nicely, so that pump will be attenuated at least 100 dB. Then all this generated entangled photon pair you can take out, extract them, and you can use all the unitary operation, quantum logic gate operation you can use using all the classical components, of course. Only thing is that you need to know how you are controlling your quantum state. That thing, all the unitary operation you need to know. And finally, after getting all the operations, you need to detect somewhere quantum state to check your quantum information processing, how much performance is there. You need a photon detector, and that photon detector also needed that single level. One particular photon comes, and that one particular photon should be detected. Okay, one photon came. It should not be that, okay, just at least 100 photon comes, then only sensitivity will be up. So you need a very high sensitive single photon detector, so that single photon can come and it will immediately give some kind of pulse, so that you realize that, okay, photon is coming. Okay, and then you can also manipulate whether the photon coming or not, depending on your calculations will be all the quantum state manipulation. I'm not going into the major theory on that, but these are the things people are targeting. So what all the things are here, if you see apparently that it is as if it is possible to fabricate in CMOS technology, but the problem is that even though theoretically people demonstrated that pump removal filters can be designed up to 200 dB, but experimentally people could achieve up to 40 dB. Okay, because of a lot of coherent scattering happens inside the device structure, how much pump is there, all things are there, sidewall roughness, all those type of things are coming. That's why it was not possible. That is actually one bottleneck people are facing now. And what else? The single photon detectors, that is actually so far all the technology available, that is only possible if you use a superconducting nanowire, and that should operate at a cryogenic temperature. So you can fabricate here, but the chip has to go into a cryogenic chamber operating less than 2 Kelvin things. And another thing is that I was talking that for controlling all these things, all these circuit, different boson, different phase control, everything you can do using a controlled circuit here, electronic circuit, that can be co-integrated. However, whenever you are designing an electronic circuit on chip, and then you have a single photon detector that should operate at cryogenic temperature, the entire thing, if you put in you need to put in a cryogenic chamber, and you need to again see that how your electrons can work in that cryogenic temperature. So all these bottlenecks are there. So challenge in front of us is that first thing is that you need an efficient photon source, you need a pump removal filter, good pump removal filter. All other things are easy. And single photon detector also fabrication wise, technology wise easy, but operation wise you need a low temperature. So you need to find a material and some good property, so that this single photon detector can operate even at a room temperature with a very high efficiency. Okay, so at least theory says that you need efficiency should be close to 90% or so. So at least one photon comes, you should have actually 90% probability that it can give you a signal. And control electronics, control electronics, normally, any IC you get at room temperature, maybe plus minus up to 75 and maybe minus 18-degree temperature, it can operate. But actually close to 0 Kelvin temperature operation is very, very difficult. 2 Kelvin, less than 2 Kelvin, that is very difficult. Okay. So all these things are challenged and progressed a lot. This photon source, people try to make this probabilistic to deterministic, all these things are coming, a lot of publication. If you are just interested, you just hit silicon photon quantum photonics, you can find every month hundreds of papers are coming for silicon photonics. And also there are 3-4 startups are already there, so they progressed a lot. Many things it is not exposed, so it will come once the processor is ready, it will come in a year or 2 years. So we what this area, that's photon source and pump removal filter, as I mentioned. And I want to skip this detailed things, is that instead of spiral waveguide, we use a high Q ring resonator. That high Q ring resonator can create an entangled photon pair generation. Also, it can attenuate whatever pump you are injecting. But that is not sufficient. You need additional structure, DBS structure. So I want to skip this theoretical part, because sometimes when you need to go for a photon pair generation, you need to operate this ring resonator at a reasonably high power. So when you operate at a high power, some other factors comes called bistability. So because of the bistability, it is very difficult to hold your resonant wavelength. Your ring resonator will be drifted, and that drift also shows some kind of memory effect. So how you are controlling your phase in the forward direction or reverse direction, depending on there, how much power will be stored inside, that depends. So we had we have integrated a micro heaters here, and we could program it, and to keep it controlled, you can program it so that if your bias condition is such that you can actually you can oppose the bistability condition to enhance the power inside, so that you can get your photon generation rate can be increased. So that thing we have demonstrated that type of device, and we have published one paper in 2021. So if you are interested, you can just download this paper, you can get also this thing. And then, as I mentioned, that on-chip filter, people tried many ways, many different design, and not a single DBR structure. They multiplex incoherently multiple DBR structure to give extinction. There's a 4 different DBR structure giving here extinction. If you see, it's starting from 20 to 70. So 50 dB extinction. This is the stop band they are getting, about up to 50 dB. And very recently, whatever we recorded, our world record, I just wanted to show here. Here we just demonstrated a DBR only single stage. We don't need to go for 4 stage. That's some kind of design we improved, and we get up to 65 dB, not only for rectangular type of grating structure, but sinusoidal structures. And here in the inset, you see that how we characterize this type of characterization setup. I think Vinu was asking that if we can show some live demo how in the lab device is working. I think here you can see the picture, that the fiber coming input. This is a probe, fiber probe coming. It's like a contact pad. How you get a electronic device, if you characterize, now you need a contact pad, and you have to give a bias signal, and then you get an output in the spectrometer or oscilloscope. You get here also, you get a optical signal comes here, fiber, and connecting here. We have a special type of design device called vertical grating coupler. So standard single mode fiber comes, and you just put on the top of it. It is like a contact pad, light will be automatically coupled. Only thing is that because the area core of the fiber is 10 micrometer. So this area also you have to little bit adiabatically expand it to 10 micrometer. So within 10 micrometer, the coupling efficiency, best coupling efficiency in our lab, we have demonstrated up to 6 dB coupling loss. So, but internationally, people are going for different design. They are going for 5 dB also, they reported. That is the case. And using this DBR structure, actually, I just wanted to show that if your pump and signal is there, is a 4-way mixing process required for your quantum qubit generation. If signal and pump that is outside the stop band, then you get a daughter photons generated here with a stimulated emission. But when this pump photon, it is going to the filter region, you see that is actually dropped about 65 dB. It is shown here in stop band. and your idler also is getting off. So this you need to understand a little bit of theory of so-called Fourier mixing process. I'm just skipping this part, and I just want to highlight a bit on so this quantum things is one of our cup of tea. That's why I just saw that that particular area is growing, and we are investing a lot of time in things. But over the years, I saw that there's many application areas there. I just try to present here the Google Scholar article search. Just if you search integrated photonics, and I just clap every year. So you see, this is started in 2000, where actually industry like Intel, IBM, HP, all those things, billions of dollars they invested in silicon photonics. That is the time. From that time onward, you see published article only on integrated photonics search. If you see, it was 590. It is actually grown to 10 times. So in 20 years. And interesting observation, I found that integrated photonics, it is growing exponentially. That's very good. And then Google Scholar article, if you just search this photonic integrated circuit, you see almost flat. It is not growing like that. So this is because, you know, this photonic integrated circuit, you need a CMOS foundry, you need an advanced technology. Only those who are having the technology, they are actually continuing. You cannot do a circuit level design fabrication in an academic institute, in an academic fab. Even our lab is one of the best lab academic institute. Even many other abroad also you cannot find that type of lab. Even that lab, if we want to integrate more than 10 components, it is a challenging task. We can improve 10, 20 or something like that. But if you go for thousands of device, optical component to be integrated together, it's a very challenging. So you need foundry access, that is actually most important thing. So I think better late than never, India government now is looking for foundry and giving a lot of incentives, and a lot of interested parties are coming out. Hopefully within next 2-3 years, we'll have foundries also, so that we can design and we can get it fabricated here in India, and we can test it, and we can contribute a lot and participate. Our ecosystem can be grown up. For the moment, we just do also, we are just collaborating with a Singapore foundry, and we are getting some chip fabricated complex design, and we are testing. And okay, that is the Indian scenario. Just to talk that just there are it's not that as I mentioned that we are just limited by the technology. Only few IIS Bangalore, and we have the silicon photonics fab basically. But other than that, there are many young talent. They are my juniors and they are good friends. I know they have studied, they did their PhD in very good places, and they wanted to return back to India to do work here. And starting from IIT Guwahati, Delhi, Dhanbad, Kharagpur, everywhere, all the people are there. They are as good as us. They can contribute much more. They have, for example, if you see me, I worked in lithium niobate integrated optics. I switched myself into silicon photonics, and because of the facility we could create here, we could reach up to certain level. But these people actually originally work in silicon photonics foundries, and they returned back. But because of the lack in facilities, they could not do. So, but thing is that also we need to drive, and we need a lot of tenacity to convince, pursue our government to get fund, to get lab facilities, then only possible. Hopefully things are now in the Indian silicon photonics, Indian semiconductor mission also, silicon photonics also has been counted, that has been included. So if someone interested, some silicon foundry also may come, then we will be able to sell more, and we can participate. At least people are saying that by 2026, I think some text is missing here somehow. By 2026, in another 4 years, so the photonic integrated circuit market is going to hit about $3 billion. Okay, so with this, I just I think something is missing. Yeah, so something is there. So just talk summary, and I must acknowledge the funding agency, host, and our facilities, and yeah, so Center of Excellence we got, and we have so many research students. I have just shown research scholar, technology staffs, and they are contributing. And if you are interested, also you just come forward and write me, and we can be part of that. We have the facility, and at this point of time, I must say that we don't have any lack of funding, particularly for our projects, etc. If we write a good proposal, government is also coming forward. They are giving fund at this point of time. Only thing is that you cannot just keep on complaining that I don't have facility, I don't have facility. You have to write proposal and you have to go forward, and so now things are moving forward. So I could somehow transfer the message what I wanted to. With this, I just hand over to the organizer. Thank you very much. If any questions, I can take up some questions here, please.
Thank you, sir. If the participants have any queries, you can either put it in the chat box or unmute yourself and speak up.
Professor Bijoy?
Yes.
Especially in the case of the grating structures, considering the temperature sensitivity of silicon, so how do you manage the temperature effect in the structure?
Yeah.
Is it something like a micro heater kind of thing, or anything else?
So this temperature sensitivity is not only is a problem for grating. You are talking about DBR structure or grating coupler?
Yes, any grating or DBR.
DBR structure, yeah. So you see, normally silicon is a very good thermoptic material. You see that very good thermoptic material means any temperature fluctuation, you can see some refractive index change. Any resonant device, DBR structure, everything, they will be detuned. That is for sure. That temperature fluctuations will be there. But actually, for actual circuit, so there are models. So you can have some kind of feedback loop. You can tap a bit, and if something drifting, so you can give a feedback control, PID control type control circuit you can design, and you can stabilize. That is one thing. And any electronic circuit also, you need to control the temperature within 0.1 degree. So photonics device also, you need a control device. And if you ask me how we are doing, we also do have a temperature controller. We also control the temperature. But normally, if you just measure your device very fast, so you don't need to bother about temperature control. But long run, because temperature, this fluctuations, that's actually a very slow process, microsecond to millisecond. But your data processing, everything that is at a very high speed. So normally you can overlook it for lab level measurement. But for circuit level, everything, one need to go for any resonant device, DBR device, etc. You need a temperature control. That is for sure.
Okay, thank you.
Next, we have a query by Panvaram. How to contact respective team if we have project proposal?
How to?
Contact respective team if we have project proposal.
How to, I mean to say, how to
I think that's what I have answered. If you have, good ideas, you can submit as a proposal to MIT, Government of India. That is one source of funding. There is a working group on photonics where myself and Dr. Das also member. Yeah, we are members. So if you have good program proposal, there is a format. It is available. If you need any email ID and all, I will be able to provide. So that is how it is. But yeah, I have a question to Dr. Das, or two questions, I think. One is, for these attendees, I think majority of them are MTech and MSc Photonics from Cochin University Science and Technology, as well as Kerala University and all. So if they want to do a project, or they are finally a project, or some internship, is there any provision? Because some of them may be interested in pursuing silicon photonics after their MTech. Maybe I think most of the students from these institutes are going abroad now. Like you may be knowing, they are all doing very good. So as an internship, is there any provision they can work in your group, and so do you really take up such things? I think that is I'm asking on behalf of Professor Kailas now.
Okay. That's it.
Thank you, sir. Thank you, sir. That question.
Thank you very much for putting up this thing. Actually, I as far as I remember that we have a MOU signed with the QSAT as well as with IIT Madras. So anyone pursuing their MSc Photonics in MTech Photonics there, and they can do one-year project here in IIT Madras if they contact. So through that they can come. Even Silicon Photonics also, if they are interested, because we don't have earlier. I think we are not allowing that someone coming outside. We would not allow use here project. We can co-guide with your faculty there. That is one option is there. So one particular problem I would say, whenever someone coming, just directly putting them into experimental handling clean room facility, that would be difficult, because anyone joining as a PhD student also, so we need to train them for first 1 to 2 years, so that they can, because all the facilities
so expensive. Yeah.
So that is the thing. Only thing is that they can come and they can work with our PhD student with a design aspect. They can learn a lot of things. They can go to process lab, watch how it works. Characterization lab, they are open. They can fabrication, they are open, that type of thing. But if you want to be skilled for the processing lab, that is difficult for 1 year.
That is reasonable, I think. That is reasonable.
Another thing is the internship. Actually, we are planning to float an advertisement that at least every year for this center, we will be taking at least 5 internship for summer internship.
Okay.
Anyone interested to get exposure to work with our senior PhD student, most welcome. Thank you very much.
Okay.
Next doubt is by Ms. Minu Jiju. She wants to know the challenges in this field.
Yeah. So that is challenge. I think you see, normally I would say that instead of challenge, I think there is opportunities in this field. I will explain. I will give you a story. I have graduated, whatever PhD student graduated, my first PhD students also, first 3 PhD students in Silicon Photonics, they are from Kerala. I think Sujit, Ramesh and Sumi, all of them actually they got, before completing their PhD, they got their job or postdoc offer. Okay, so it is an opportunity. Challenge is there. I think there are many challenges I discussed. That, for example, if you are going for quantum photonics things, so a lot of problems are there, particularly thermal stability, this type of thing. You need a solution. We need young talent to think and come out with a better design to give a better solution. For example, we need a DBS structure which can give 100 dB extinction. We need a device where generation rate will be much higher than what we are getting currently, photon generation rate. Or modulation for phase shifters. Phase shifter, for example, you need thousands of phase shifters to be integrated. Okay, and the thousands of phase shifters, how you can integrate? If you integrate normally each of these phase shifter, if it is eating maybe 10 to 20, 30 milliwatt of power, the thousands of phase shifter, it can just multiply 1,000, that much power hungry. So you can design a phase shifter where you can power consumption will be much more lower. So those are the challenge, and that is why actually there are thousands of, if you just search Silicon Photonics job, there will be finding thousands of jobs, mostly in Europe and USA. Unfortunately, India ecosystem is not there. We don't have anything, but we have only few places. We are just trying very hard. So things are moving, but once you are in, you don't think it is a challenge. Challenge, of course, there you can solve, you can learn, but job is actually, it's a no issue at all. So, for example, for even now, we say I I got a email from, I think you might be knowing Ajay Jacob from ISI director, University of Southern California. He is looking for someone immediately. He is asking that any students graduating from our lab. Okay, so that is a very hot area, and only challenge is that you have to just maintain your facility and resource, all those type of things, so that you can get that. That is the challenge only, nothing else. Otherwise, as a student, I would say this area is an opportunity for you.
Thank you, sir. One of the participants want to know about your opinion about forming a network in India for silicon photonics.
Yes. So we tried one point, and we are also keep on trying that thing. I think this is the facility we are creating for this center of excellence, and we would like to have collaborators from various institutes. And once everything is streamlined, and we can go for some collaborative work, that is possible, and that I think very much needed for India actually, because this type of facility you cannot just establish everywhere. It's so expensive, it's very difficult. So we should have that type of network, and we have some kind of commitment in that direction also. Some of our good friends, we are working, but things has to be streamlined. Yeah, that is actually very much needed, and we should do that. Sure.
Sir, we have a time limitation, so we will wind up this one because next meeting will start at 7.
Okay.
Okay. Thank you.
So we have to thank formally. Yeah.
Yeah, Sandra.
Thank you, sir. Yeah. On behalf of the Photonics Society chapter, the Kerala section, and everyone present here, I extend our gratitude to Professor Bijoy Krishnadas for the enlightening and informative session. Thank you, sir, for covering the history of silicon photonics, its current status, and future prospectus. Thank you.
Yeah, thank you very much. Thank you very much for this.
Yeah.
Thank you, sir. Thank you.
Sure.
I would also like to thank each and every one of you present here for making this webinar a success. Thank you all. Have a great evening.